All right, we got ELE 115, Electronics for Technicians 2 here. This is a hopefully a short video on a review topic for ELE 110, Electronics for Technicians 1. Just taking a look at a simple series circuit called a voltage divider. All series circuits are essentially voltage dividers. If you remember, we made the point in our Ohm's law interview and our kind of review of series circuits, that in a series circuit you have one current, and that's that current flows around this loop, and there's no other place for this current to go. We have an output here, but we don't, there's nothing hooked up to it. So we have one current that can flow. You could call it I total. You can call it IR1, IR2, IV1 if you want. But it's the one current that flows, and that current flow will produce a voltage drop across R1 and a voltage drop across R2. And those two voltage drops have to add up to whatever voltage rises we have in the circuit. We only have one voltage rise, it's V1 here, and it's 8 volts. So, and I think I probably should have called this VT, but I put a note up here and called it VT, so that should do just fine for us. So we have a series circuit. We can look at the total resistance first. R total equals the sum of the resistances. Here it's 3.3K plus 4.7K gives us 8K ohms. V total is 8 volts. So the total current that's going to flow here is the total voltage applied to the total resistance. And that's going to be from our Ohm's law triangle. Remember, V is on top and IR are on the bottom. So if I put my finger over I get V over R, and I get that I total equals 8 volts divided by 8 K ohms, which is essentially it is 8 volts divided by 8,000 ohms. And so I get 8 divided by 8 is 1, but when you have 1,000 in the denominator, I get 1,000th of an ampere. You can write that as 1 times 10 to the minus 3 amperes, but 1,000th of anything is a milli, so that's a milliamp. If you think about a meter, you divide, that's just a little bit bigger than the yardstick. You divide a meter into 1,000 parts, you get a millimeter, and that's you'll see those on rulers, and I'm sure you've experienced that. So. Let's look at the voltage across R1. We now know what the total current is. It's 1 milliampere, and that's the same as the current through R1. So we can say VR1 equals IR1 times R1. Again, the Ohm's law triangle, V is on top, I and R are on the bottom. So I cover over the V and I get I times R. So I'm doing that. And IR1 is actually IT, so I can say that this voltage VR1 is equal to IT times R1. 1 milliamp times 3.3K, that's 1,000th of an ampere times 3.3 thousand ohms. The 1,000th and the 1,000 cancel out, and I get 3.3 volts. Likewise, I perform the same calculation, the same thing happens, and I get 4.7 volts. And I add up these voltage drops. They're voltage drops because the conventional current arrow would enter, we would write this as a plus and a minus. Arbitrarily, we would define this as a voltage drop to begin with. So, and the current would enter on where we would put the plus sign, leave on the negative sign. Again, we'd have a plus sign here. Conventional current would enter and leave, and that's just the way we drew the circuit. If we put our plus signs and minus signs differently, it still works out. Kirchhoff's voltage law works out, but some of the signs would be different. Now the current comes around here, and as we enter this battery, we because of the way we conventionally do things, This guy will be a voltage rise. Current will enter, the current arrow will point into the minus side and out of the plus side. So our total voltage rises is minus 8 volts. We always declare voltage rises as negative. And our total voltage drops is plus 8 volts, and we add those together and we get 0, and Kirchhoff's law is satisfied. So, let's be careful here with what we're doing. Now let's look at the individual voltages here. So, and let me just turn to the simulation. So I ran this in a simulator, and our total voltage here is 8 volts. You can see it says 7.8. This would be 7.9. This would be 8, and that is 8.1. But if I were to put my cursor on this thing, it says 7.988, 7.997. It is 8. You can fool around there. I got 8 volts. It's indicated right at the top of this little oscilloscope window. And this is a classic, what we call DC circuit. It's more than just DC. It's completely static DC in that, there's no pulsing or anything on our voltages. So V total is 8 volts. And if I go to V out, that is essentially the voltage across R2. That's VR2. And we see that voltage as, let's see if I get this right. Sorry. I had it for a second. I had 4.700. Obviously, the scale is pretty touchy here. But you can see that is, you can convince yourself. There we go, 4.7 volts. Okay. And then we have the current plotted also. I have IR2 up here. You see right over here, IR2. And that value is very tough to land exactly on it. But you can convince yourself that's 1 milliamp, and it comes over here to where the current scale says 1 milliamp. And so that agrees with our prediction. If you want, we can add a trace here. Add traces. And I can put, I think we can add, we have VT and V out, but we can make up an expression. We can say V R1 is equal to V, it's equal to the voltage. Now let's do it this way. Yeah, VR1 is equal to the voltage V total minus the voltage of V out. Okay. I have to put the parentheses around the R1 here. Unknown voltage requested, R1. Well, heck. Do I get to do this at all? I thought I could. Maybe I can't. Oh, I don't have to give it a name. It's just total voltage minus V out. And so we put that in there. And if we go and look at this thing now, it's this green. See up here it says V total minus V out. It's this green wire. And let's see. Well, 3.302 is close enough. So we've proven that at least in the simulator, we would get 3.3 volts across here by subtracting V total minus V out. That gives us a voltage for that. And V out is, with respect to ground, is the voltage across R2. 3.3, 4.7, add them up, you get 8. That's great. Kirchhoff's voltage law is satisfied, and our calculation on current was correct. So the whole idea of this voltage divider, that's what we're doing, right? The voltage drops across each resistor go as that resistor's portion of the total resistance. It's just the way the math works out, you know. This guy here, this resistor here, gets 3.3K out of 8K worth of the total voltage, 8 volts. So he winds up with 3.3 volts. This guy gets 4.7K out of 8K worth of the 8 volts. And so that becomes 4.7 volts. And I just picked the math so it would be easy to prove this with 1 milliamp. So there's this thing called the voltage divider rule, which we'll get to, but it's just a way of writing the work that you would otherwise do. But when you look at this circuit, by inspection, you can say, oh, this guy's gonna, you know, this is just a bit more than the total, half of the total resistance. You know, the total resistance is 8K, 4K would be half of that. This guy's a little bit more than half the total resistance, so he's going to get a little more than half the total voltage. This guy's a little less than half the total resistance, so he's going to get a little less than half the total voltage. So if you take, let's see, R1's portion of R total, 3.3 over 3.3 plus 4.7, that quantity, I get 3.3 over 8 is the portion, you know, kind of like 3/8. VR1's portion of the total voltage is 3.3 over 8, right? 3.3 volts over 8 volts total. So it works out. The voltage goes, and again, this is nothing magical. Just it happens because the way Ohm's law works and is a you know, kind of straight linear relationship between three quantities. Larger resistances in series, the larger resistances are going to get a bigger portion of the voltage, and the smaller resistances are going to get a smaller portion of the voltage. You know, if this were 7K and this were 1K, we'd say, well, see, they add up to 8K, I'd still be getting 1 milliamp around this loop. And this guy would get 7 volts, and this guy would get 1 volt. And, you know, I could do that and rerun it. I'd rather not change that stuff right now. Oh, what the heck. Let's do it. Let's call, just for now, let's call this guy 1K. And let's call this guy 7K. And let's run this thing here. And we'll go to our thing, and it looks like we got V out. Where is everything now? 7K and 1K. Oh, I've got to go do this again, sorry. So I press this here, I press that there, and I grab this current. Okay. So here, the total voltage is still 8 volts. All right. The V out is now 7 volts. Again, you can look up in this area right here for when I'm over the line. So there's 7 volts exactly. And the current, IR2, which is the same as our total current because it's a series circuit. That guy is, it says 0.998, and there we go, 1 milliampere. Okay, now don't mind the voltage thing, that just tracks wherever the cursor is. And then this guy down here, 0.991 volt, there we go. Well, you can see he's 1 volt because he's, well, if you want me to, I could always do this. Could zoom in, put my cursor on him. There you go, 1 volt. All right. And okay, excuse me. So Again, the voltage divider rule is just a simplification of the Ohm's law analysis. And what it says is that, you know, we would have gone here and calculated the total resistance. RT equals R1 plus R2. And that's just what they're doing here. Essentially, they're calculating, you see this part here that says VT over RT? Well, that is your total current. Then you multiply it by whichever resistor you care about, and you get the voltage. You get the voltage across that resistor. So VT divided by RT is IT, and then you multiply it by the resistor you care about. There could be 5 resistors in here to make a series circuit. All right. So you pick out the one you want, and it's just like I said, it's a simplification. It's nothing mysterious. But the voltage divider rule is good to remember in practice because you should be able to look at a series circuit and just say, oh, there's a bigger resistance, that's going to have more voltage. There's a smaller resistance, that's going to have less voltage. And sometimes it'll be that there'll be a really big resistor and you say, well, that's going to dominate. Most of the voltage is going to be there, and it helps you kind of see what the circuit's going to do. I'm just going to save my circuit again. So that's the voltage divider. It's just a type of series circuit, and the voltage divider rule is something that expresses that, but it doesn't save you a ton of time. It's just a way to look at series circuits. And you know, if you do remember this formula, it's fine. If not, and you're moving through your circuits, it's not going to save you a ton of time, but it does capture the gist of the idea that bigger resistors in a series circuit have more of the voltage across them. Smaller resistors have less of the voltage across them. And of course, all that voltage around that loop has to add up to 0, adding voltage drops and voltage rises. That's Kirchhoff's voltage law. Ooh, there's a spelling mistake. I am so sorry. 2 H's in Kirchhoff. Okay. How does it look now? Good enough. No, it's not good enough. Of course it's not good enough. A little better there. Okay. Kirchhoff's voltage law is satisfied, and we can all rest comfortably in that. Alrighty. I will put, I'll put this simulator file in case you happen to be an LT Spice aficionado. You'll have this, but of course also have a video of this fantastic presentation. Take it easy, and we'll see you next time. All right? Bye.